Pictured here is a half-wave diode rectifier. This was presented in an earlier video, and nothing here has changed so far. Note these formulas. Peak, that is the highest point on the half cycle. And when I say half cycle, only half of the sine wave is utilized, the other half is lost. Your RMS voltage is 12.6. RMS times 1.414 will give me peak, which is close to 18 volts in this case. Average is the DC equivalent power transfer, and that's peak times 0.637 divided by 2, or RMS times 0.9 divided by 2. So this is a half-wave rectifier. Now we come to a silicon-controlled rectifier. We can do the same thing, but now we have a third element in this, in a gate. We have the anode and cathode as before on a diode, but now we have a gate and a diode. We can turn it on and off with a gate current. If I press PB1, this will turn on, and the waveform across my light bulb, which is my load this time, is half wave. Everything else on average, RMS, and so forth is exactly the same. Note that the gate must be triggered from the anode side of the circuit. Let's look a little bit closer at how we can use this with AC. Here is a redrawing of my circuit from the earlier slide, simplified so you can see it better. As far as the load goes, the load does not care if it's in the anode side of the circuit or the cathode side of the circuit, but the gate current still has to come from the anode side. If I push the switch, it will conduct in this way only during the positive half cycle. Now I have inserted a variable resistor or potentiometer in to replace the switch. As I adjust the resistance on the pot, I change the amount of current that gets to the gate. When the sine wave voltage climbs high enough, we hit what is called the trigger threshold or breakover voltage. From then on, it will conduct and continue to do so until the sine wave goes back to zero. This is something you have to note, that once the SCR is turned on, it will continue to conduct until you either break the current path or the AC sine wave goes to zero. Now we have an SCR connected to a DC circuit. Of course, it's not marked here, but that's the anode, that's the cathode, this is the gate, and it's being triggered from the anode side again. If I press S1, the light bulb, of course, will turn on. But if I release S1, it will stay on. This is one of the problems you're going to run into with both triacs and SCRs, since triacs are built from SCRs, as we will shortly see. The only way to cut the light bulb off is to press S2, which will break the current path and turn off the SCR. This is handy, for instance, in using burglar alarms, where this might be a window switch that switches on the alarm, but you cannot turn it off until you hit the reset. So remember, if you have a DC source and you are using it with an SCR, it will not turn off until you break the current path. As we discussed in another video, this is full wave DC rectification. That goes from AC to producing pulsating DC. Just like the formula for peak, it's the same as in the half wave. And the average voltage, that is equivalent to, say, straight DC, as far as power delivered to the load, it's about 11.4 volts out of a 12.6 volt AC source. Here is the same circuit you saw before. Now it operates the same way as it did before, other than a half-volt voltage drop across the SCR. But now I can turn the full wave DC on and off by utilizing a silicon-controlled rectifier. Press SW1. There is my full wave pulsating DC delivered to the load. Now we're going to be introducing you to another type of silicon-controlled rectifier. This is the light-activated silicon control rectifiers, or LASCR. Instead of a small current to the gate, we have a gate element that when exposed to light, such as from an LED or a flashlight, it switches on. Over here on your right as well, a pot was placed in the gate circuit, and it adjusts the trip point for when the light hits it. These are just not seen much today outside of as individual components. They are used more in what we call optocouplers. In this plate, we're seeing light-activated silicon-controlled rectifier that is contained within an optocoupler that includes a light-emitting diode. This gives us the advantage of connecting a higher voltage AC circuit, such as this on the right, with a low voltage microcontroller such as Arduino. The H11CXX and 4N40 series optocouplers use light-activated SCRs combined with an LED. Here we're using it to control a small lamp. Now, one thing to be aware of with these optocouplers, they are low-powered devices. This is a low-watt lamp. You are not going to be running 100-watt light bulbs with this. But we can use this to drive higher-powered devices. Here I illustrate how to use an Arduino microcontroller in combination with an SCR-based optocoupler to control pulsating DC to a load through a higher-powered SCR. I'll have a separate video on how most of this works, but it's based on this circuit up here that produces what is a zero crossing pulse, and using Arduino's interrupt system, we can control exactly where in the sine wave I can fire U2 and the SCR combination to control the exact amount of power delivered to my load. Knowing that an SCR is a unidirectional device, or only conducts current in one direction, we can take two SCRs connected back to back, as shown here on the left, cathode to anode and anode to cathode, and tie the gates together to have a solid-state switch that will conduct in both directions. Thus, what I end up with is a solid-state AC switch, commonly known as a triac. I have a completely separate video on that explains how to use those. But to summarize, a triac is two SCRs back to back. And just like you have to trip an SCR from the anode, you have to trip the gate on a triac from MT2. But more on that in the other video. Now in this slide, we're using a SCR-based optocoupler. And of course, SCRs being unidirectional devices are not going to interface directly to a triac, which is a bidirectional device. But by utilizing 4 diodes as a diode bridge and connected as shown here, when I switch on the SCR-based optocoupler, I will fully switch on a high-powered triac that will control an AC load. This is another variation of the circuit here, even though it's not shown internal and will be looked at in the triac video. This is an internal photo triac that works like a photo SCR, but it's bidirectional. But you notice that we're using two SCRs out here back to back with these associated components. This way I can use two heavy current SCRs in this back-to-back configuration to control very high power AC loads. Okay, that's the end of the slides. There will be a short video showing the waveforms from my oscilloscope as an SCR Arduino-based circuit controls the phase angle and power output of pulsating DC. Thanks for watching the video, and catch the others in the series.
Alright, what you're looking at again is my oscilloscope. On the top of the video you will see full wave pulsating DC. The bottom half of the video is where I'm using AC phase control with a silicon controlled rectifier, or triac, if I'm using a diode bridge, to control the on time of each half cycle. If you look here, you have full power delivered to the load. There, as you can see, is no power delivered to the load. The secret is that you're going to detect the zero crossing pulse, which in this case is here or wherever. Then you're going to delay a specific set time delay before you trip on the triac or SCR based on a potentiometer that's connected to my Arduino Nano. Yep, this is being powered by an Arduino Nano. Both the zero crossing detector and the drive to the SCR is done through optical isolators in order to protect, once again, the 5-volt circuitry. You just cannot get around opto isolators for power and flexibility. Let's move